And we're live. Good morning and thanks for joining us. We really appreciate you making the time this morning. My name's Andrew. This is Mark Terryberry, of course. How you doing, Mark?
Doing good. It's a little bit chilly out here, but not bad.
Yeah, just cooling off here in Camarillo, but we can't complain, right? We're not in the Midwest or something.
No.
So we've got a really cool show for you today, for sure. As the byline showed, we're talking about lathe insert secrets today, and kind of probably one real secret in particular today. When we were talking through this in preparation, we were talking about how we weren't going to bury the lead on this one. We were just going to come straight out and say it. So, do you want to say something before that, or do you want to just jump right into it?
Real quick. We end a lot of our videos with that tagline saying, thank you for letting us be a part of your success. And that's kind of what this live stream and most of our live streams are about, right? They're all trying to help you succeed. And we're giving you information to help you make parts easier and make your life easier. Now, what's unique is that today's live stream is just critically important, really important, I think, for lathe operators as well as lathe programmers, the people that are buying inserts, but then oftentimes the guy at the machine, the person who's actually running the parts, is left to make quite a few of these decisions himself, deciding whether to run this insert and this insert. And so we're going to show you pretty quickly today the differences and how you can avoid stringy chips. That's kind of the basics of today. So this is one of those ones that you're going to want to come back to on YouTube, watch again, have your operators watch, and then apply this information the next time you go and buy inserts. Frank, if you could give us a little teaser of what we're going to be looking at today.
Actually, right before we jump into anything like that, let's just say that if you got comments or questions, just throw those into the chat. We'll be glad to answer those if it makes sense along the way. And of course, we'll answer more at the end when we're done with the whole presentation.
Yeah, that's the beauty of being live, is we can fix our mistakes as we go.
That's right. Okay, sorry about that. You wanted to.
Oh, that's perfect. No, here we go. Okay, so look, on the top of our screen right now, we've got a bad chip situation. On the bottom of the screen, things look good. Now, what's crazy about this is that this is the exact same program, same feeds and speeds. We got the same depth of cut. Everything is identical about this except for one thing. And this is kind of the point of today's video, is talking about chip breakers. There's a different style of chip for every material type, every depth of cut, this type of thing. And we're going to explain this and kind of go in depth on this to allow you to run your machine, your lathe, and walk away. So if you have these big, bird's nest of chips, you can't walk away from the machine. You can't run in automatic mode. If you have a chip conveyor, things are going to jam up. It's going to become a problem. So that's what this video is about. We're going to show you what the numbers mean on our inserts, and a lot of these things are kind of ANSI, ISO standards, so this applies to all inserts, but especially the ones that we're selling here. But again, this applies to anything you might be running right now. We'll be talking about these guys.
You've got some big piles of chips on the table over here. Do you want to talk about those now? Kind of talk through what the differences in how you did those cuts were? Or?
It's going to be huge. Let's look at that. Let's go ahead and explain kind of the first half of what the chip or the inserts look like. This is kind of common knowledge stuff. So we're just going to get rid of this really quick. Talk about the ISO and ANSI standards for inserts, and then we will move on. So we kind of wrote it up on the board here, but in my programs, what we'll often do is I'll write, T101 or T505, and it's a CNMG 432. This is a kind of standard insert. This is the way that we name our inserts. And this is the point of this video, is that this information, what we all understand our inserts to be, this is only half the story. This is not the entire story of what an insert is. Now, there's lots of reasons to run different inserts. Actually, here, we'll cut to the different shapes. Do you have that slide of the different style of inserts? We got some pictures up here that we'll look at as well.
Yes.
And these guys, up here on the screen, Frank, we can also go to the microscope and show some of these guys.
First time we've ever had a microscope on the live stream, by the way.
Yeah. And we got pictures also up here that have the like the CNMG, VNMG, WMG. So obviously, this is just recapping so we're all on the same page. That we just have to do a little housekeeping here. So this insert right here is a CNMG. The C just means that it's an 80-degree insert. It's the angle at the tip of this insert. Now beyond this, we've got something that's got a little pointier angle to it. That's like we have a 55-degree insert, a 35-degree insert. We've got this is a DNMG. We've got a V NMG. We've got W inserts, which have different shapes to them. And just wanted to get that out of the way. We can cut back to the main screen here. So we have all these different inserts, and we would choose one over another based on the type of part that we might be running. If I've got these guys, Sal, if I'm running this type of part, which is just an intake flange adapter, if I tried to cut this guy with a regular CNMG insert, then as it came up and over this bump, the insert would drag, and we would end up eating into our contour. So we choose this shape based on our part. This other insert here is much pointier. Obviously, it can go up and over. So this is pretty basic stuff. We'll choose the shape of inserts that we want based on our part. And if we go to slideshow, we can go back to Milton's slide. Milton made a video on choosing inserts. It's out there on YouTube. Definitely worth taking a look at. And he's got this part that looks pretty good. We'll see here. There it is.
Yeah.
So this part right here, it just obviously the shape of the insert is why we choose them. That's good to know. That's not what we're talking about today. Just that's common knowledge that we need to learn first. Now,
right. So you're going to use different insert shapes to reach different contours. But even within the CNMG 432 series of inserts, we have to differentiate more, right?
Yeah, so we're going to get to the good stuff right here is on the other side of this line, but this is all we typically know. The C right here is the shape of the insert, right? If it's an 80-degree insert, 55, 35, what have you. The N is the relief angle on the tool. We'll talk about that. If it's a single-sided or a double-sided insert, we could spend an hour talking about these guys. The reason that we'd want to go with an N insert is that being double-sided, we might get 4 edges per insert instead of just 2 edges per insert. But it's also not as much of a finishing insert. The third spot might be our tolerance on an insert. If I've got a CNMG, the insert itself is going to be, basically it's a molded insert, and we've got plus or minus 0.03 of an inch on this guy. And so if this is plus or minus 0.03 of an inch, this third spot, something like that, then every time we change the insert, we might end up being, we might have to make an offset adjustment every time we change an insert, because these are not ground, they're molded typically. Sometimes the perimeter is ground. But if you get a C, then we're plus or minus 1 thou. The final type here is just the style of the hole in the insert. And so we would have either a set screw holding it down or a double clamp. Again, this is all the physical shape and size of the insert. As well as these numbers right here. The inscribed circle, 432, would be the actual size. 4 means 4/16 of an inch, I think. Well, it's going to be a 1/2 inch inscribed circle. The 3 is the thickness, and the 2 is the nose radius. We could talk forever about this stuff. This is a complete video in itself someday. But again, it's not what I want to talk about necessarily today. What we're going to talk about today is chips. And this is what you were talking about earlier.
Yeah, let's just get right to it.
Yeah, so the different inserts that we carry, they have different chip breakers on them. So if we have one insert, it's good for a certain depth, and it cuts out perfectly well, and another depth, it cuts poorly. And let's go ahead and do some cutting here. We'll show you one depth of cut. We're going to go and start the machine, actually. We're going to show you, I'm going to go to my tool 1. So Sal, we can come over here and get ready to run. I'll get ready to start this in just a second there. I'll let you sneak in there. So what we're looking at here, the speeds and the feeds don't matter too much. What I'm really looking at here is the depth of cut. And we're going to see what this guy cuts like. So this is pretty boring, but it's going to make the point for us. This insert that is in here is it's a CNMG 432. Nothing fancy about it. We're just going to let this thing run. And we'll come back to this in a second as it runs in the background, and we'll come back and open up the door. But what we're talking about here is that CNMG 432 is not enough information to make a decision on. Your depth of cut and the material that you're cutting on are also critical. So I'm going to let this thing run 3 or 4 passes, so it's a little bit boring. We'll cut back and forth here as we come back. We'll check back in with Sal here in a minute after this machine has made several different passes. What we're going to do is we're going to change the depth of cut. Right now we're taking a fairly shallow depth of cut on this part, and we're not breaking a chip. It's not a great shot at all. Now if we come out to, let's go to the speeds and feeds chart.
Okay.
So this is where we live as programmers, but it's also where we need to live as operators, because if a programmer says CNMG 432 in the program, again, that's not enough. This right here is right off our website for Haas tooling. All of our inserts will fall into one of these categories. And right now
this is what you're running right now, right? You're running the HUR.
This is the HUR insert. So I'm running right now, my material type is a 4130 material, I think. Left over from a trade show demo. And so we're running that material right now. It could be 4140, it could be 1018 as far as I know, but it looks pretty shiny, so I think it's 4130. The point that we're trying to make right now is if, and we can zoom in on the next, do we have the other slide also?
You want the HFF or do you want the?
Just say HUR, whatever, either one, this is fine too. Or you can just zoom in on this guy.
Okay.
So what we're looking at here is, this is a depth, how deep we're going. Are we gonna go 40 thou deep? Are we gonna go 160 thou deep? And right now, we're going pretty shallow with this depth of cut. If we can cut back the machine. And we're just letting this guy run. We're going pretty shallow. Now, typically we'll go shallow for a finish pass, less deflection, and we'll go deeper for roughing passes. But if you're trying to use the same insert for roughing and finishing, this is what you're gonna get into. So this right here, this insert is its sweet spot, its happy place is above or deeper than about 45 or 50 thousandths of an inch deep.
At least that deep.
At least that deep.
Right.
This thing can go 200 thou deep per pass. Now, if you go shallower than this depth, then you're going to end up with stringy chips. So if we look at the microscope here, and we'll get ready with the 3 lines, with the lines on this guy. So looking at this microscope, you can see that there's a different chip breaker on this edge. What this insert is built for, this is our UR 80. This insert, if you try and go this deep, you're going to get stringy chips. It needs to go at least this deep in order to break a chip. If you wanted to go shallower than this, you would need to switch to a completely different insert. And so each of our inserts, it basically is a different, almost a different snowflake shape to it. This insert is meant to live at a shallower depth. If I'm only going a little tiny bit here, that's where this insert wants to cut, and it's happy doing so. And we can cut to Andrew's shot here on the screen. And that's what we're looking at right there on the screen, is that these different grades have different happy spots, different sweet spots of running. And you need to choose your insert accordingly. I think I'm going to stop the machine in a minute after this next pass. We'll let that thing stop in a second. We'll show you what the chips look like. We'll make a depth adjustment and then rerun this part one more time. But again, this part right here, this is an R, which is a roughing insert, an HUR roughing insert. It loves, between 50 and whatever 200 thou depth of cut. That's where it wants to break a chip. Oh, that's kind of funny. In some strange way, I didn't draw these lines properly. This is a perfect happy mistake. When I put these lines on there, I'm drawing this thing like this. I just realized that yes, while we can cut very shallow, it's not where its happy spot is. This part, really needs to be like this. We want to cut between here and here on this insert. That's where we need to be. Our depth of cut needs to be start here
Right.
and end here. We need to cut at least that much material to even break a chip.
You're cutting through this entire region, but your happy ending
So this is
point
our base point, and that's it. Yeah.
Yeah. I
this
guess you
one's
could show it
happy
two ways.
cutting here. Yeah. It depends on how you think about it. If you're not going this deep, it's not going to break a chip. And we have a roughing insert, a medium insert, and a finish insert just for that guy. How are we doing here? We're going to let this thing finish up.
Like you said, that's a long run.
We can let this thing go. Now, this insert is not running very fast. But again, I'm not trying to, all I'm going to do is change the depth of cut on this insert, not changing the speeds or the feeds. And we're going to see how that affects our chips, our chip creation. So if I open up this door right now, can you imagine, Sal's smiling, he's filming this thing. Can you imagine trying to run the chip conveyor at this point? This is terrible. There is nothing wrong with this insert. This insert is awesome. The problem is mine in that I'm using a roughing insert that has a different sweet spot when I should be using a finishing insert if I'm taking that shallow of a cut. So the chip conveyor would obviously have a real problem with this type of bird's nest. So this right here is what a lot of us end up with if we try and use the same insert for our finishing passes that we use for our roughing passes. And you'll end up having a nightmare if this tries to go through your chip conveyor. In fact, I'm just going to go and shove this into the chip bin right now and get rid of this completely. And so here's our chip conveyor coming up and over, and you're like, oh, my chip conveyor gets stuck all the time. It's a terrible chip conveyor. There's nothing wrong with your chip conveyor. The problem is you're not using the right insert grade for your cut. Now I'm going to go ahead and make a change to my program. We'll rerun this guy. Actually, I got some more chips in here that I really don't want to run through. It's going to make some noise. We'll get rid of this real quick. All I'm going to do is change my depth of cut because this insert likes to run at a different depth. Okay, so again, no difference in feeds and speeds. We're still going the exact same everything. I did change the depth of cut from taking a very shallow cut to making a deeper cut, and we'll show some more of this on the video. I'm just going to press cycle start. Looks good from there. Okay, so we'll let this guy run. Just make sure it's all the same. Yeah, everything's the same. Okay, so now Sal, take a look at this.
You want to go something else here on the screen, or?
Yeah, we can show the sweet spot, the one
Okay.
slide, and then we'll come to this one.
Yep.
So what we've shown here is the only difference we've made is we've changed our depth of cut because that's where this roughing insert likes to live. If you're getting stringy chips, it's typically one of two problems. Number one, you're not going deep enough for the insert that you're using because you're out of the sweet spot for that insert, and or you've simply chosen the wrong insert. If you really do want to go that shallow, we need to choose an insert that has a different chip breaker on it that is meant for a shallower cut. And so on the screen right here, we're just saying, look, we're in the sweet spot, which means we need to be going at least this feed and speed, and we need to be going at least this depth between there and there. That's the way these charts work. And if you run your tooling in the sweet spot, you should be breaking a chip. Mm-hmm. And this is half of our job as machinists.
And you've got an audio example there of of the fact that you're running correctly now, just with those chips banging
Oh,
against
yeah.
the door, which you didn't have before. So is there also, some of the time maybe it's not so dramatic, right? You've got, maybe you're at the bottom edge of your sweet spot, so you're not, maybe the insert isn't quite operating optimally because you're not going deep enough. It isn't as black and white as like, oh, a huge bird's nest and like chips flying off. Maybe it's just a little bit of that.
Yeah, exactly. There was a little bit of stringy chip there at the very, very end, and we're going to talk about that in a minute, talking about our finish passes. Again, if you're a programmer, you want to stick around and watch this. And if you're an operator, we need to be looking at the chip breaker on the inserts. So we'll let this run one more pass. We'll stop it. We'll open the door and show you guys what's running here. This guy's almost done. We'll let it come back.
So our watching here, Rayadev asked, what material is this? And you were saying you thought this is probably 4130.
I believe it's 4130. It looks pretty nice.
It's cutting better than 10.
So yeah, I don't think it's
1018
1018.
or something.
And this is pretty cool. So if Sal comes in there and looks at this guy, again, stringy chips versus not stringy chips. The only thing I changed was the depth of cut. Period.
So what were your two depths? What was the first depth you were cutting at, and what was the second one?
Well, so the first depth of cut that I was going was basically 25 thou, which was pretty decent for.
So you were below, definitely outside the sweet spot.
Yeah. so that's a good point. So these chips right here, also I'll just mention that all those chips in the bottom of the machine, if I press the chip conveyor button right at this point, this is what we want. You don't want to have to empty out the chips on a machine by hand. Oh, can you see that? We'll see that thing. So with a simple button press, all of our chips are disappearing because that's the way it should work. And I'm going to open the door here on you, Sal. And that's it. So that's the way a chip conveyor is supposed to work. That bird's nest that we had earlier was a problem. And we need the machine to be breaking the chips so we can walk away from the machine. But what you were just talking about, Andrew, we can show here on the desk. So this right now this is a 20 thou depth of cut with an HUR insert. I got my baggies here all labeled properly. And I'll mention this earlier when I opened up the bird's nest and pulled out the chips. I was wearing Kevlar gloves, excuse me. You definitely don't want to be grabbing bird's nest chips by hand. You need to be using basically pliers or a hook or something like that. But if you look at these guys, Sal, if you can see this is the same insert. This is the chip it makes at 20 thousandths of an inch depth of cut. That's not supposed to be the depth of cut for this insert. This is 50 thou depth of cut, which is fine. That would go through the chip conveyor. It's a beautiful cut still. This pile right here is our 60 thou depth of cut. And this is where this insert really starts to come alive. When I was changing that insert right there, I think I was running 120 thou depth of cut, which is kind of right in the sweet spot for that insert. This is a 100 thou depth of cut pile. And this bag of inserts right here is 150 thou depth of cut with that guy right there. So you can just tell, it looks like this was created by separate tools. And it wasn't. It's all the exact same insert, just different depth of cuts. Not only that, but there's more. So we've got different inserts. I'll just grab them from over here. So we've got a roughing insert. This is this insert, an HUR. And then we've got this guy, which is a straight up finishing insert, which is an HFF. We could have used an HUF, but this is an HFF finishing insert. And with the exact same depth of cut, if we just change the insert to an insert that was meant for this depth.
Right, so now you've got your shallow depth of cut, but you're using a different insert that's made for that depth of cut.
Oh, exactly. So these chips right here are at 20 thou depth of cut. let you see this difference here. What a mess I'm making. This stringy chip and these chips were made with the exact same program. Everything's the exact same because that's what it's made for. This one's meant for finishing, this one's meant for roughing. Same program, same depth of cut, same feed rate, everything identical, yet we're getting completely different results because we chose the right insert. So, if we go to our board, we're only telling half the story. We've got CNMG 432, that's what we might write into our program. Now as the operator, you can't just grab any CNMG 432. If we're roughing, we would want on this regular steel 4130, we're like that. There's a million different versions out there with different grades. But right now, we're just talking about the chip breaker. We want to run a roughing insert if we're going deep, if we're removing lots of materials. And if we're finishing that material, then we would change our minds. If we're going shallow, and the result's right there. This is just basic stuff. We would go with a finishing insert of some type. And we can go to the website, and you can talk about your chip breaker, or you can just go to your speeds and feed page, and you can find the perfect insert for the depth of cut that you want to run at. And do we have a picture of the, I might change the insert for us if we have time. We'll run a different part. Do we have a picture of the SD55 or an SD40, the CL? Oh, that's okay. So the idea here is that, well, it might have been that PowerPoint also. If we're doubling our depth of cut, just the way it works, it requires twice as much horsepower. So that's it. So if you've got a 10 horsepower lathe, you can go a certain depth of cut. If you've got a 50 horsepower lathe, if you're buying some giant, SD45 or whatever, you can double that depth of cut because you have more horsepower. Just the way it works. If I go from 50 thou depth of cut to 100 thou, requires twice as much horsepower. If I go from 15 thousandths of an inch per revolution feed rate to 30 thou per revolution feed rate, that requires twice as much horsepower. If you double your feed rate, that requires twice as much horsepower. If you double your depth, that requires twice as much horsepower. So roughing on a CL, right, that's got, I don't know how much it has, 8 or 9 horsepower, 10 horsepower, 8 horsepower, something, it's not a lot.
Yeah, 5 horsepower.
5 horsepower, yeah. It's gonna be small. So this is a small machine, it only has so much horsepower, you can only go so deep with that, with roughing cut. So you're like, I'm roughing, I'll buy a roughing insert. So you buy a roughing insert. A roughing insert for a CL is quite different than a roughing insert for an ST30. Or like this guy's an ST28Y with crazy amounts of torque and horsepower. I can bury this thing all day long. And it makes a big difference. So don't just buy a roughing insert because you're roughing. Roughing on a CL is basically going to be using at best a medium insert.
And you're going to get this exact same problem.
Yeah.
You're going to be pushing that little machine as hard as you can, and you're going to be making bird nests all day.
Exactly. Right. Now, let me go to the, we can change the insert there, but we have a lot to cover here. We'll talk about it. What we're showing here on the table.
Yeah, I was going to ask you, you've got a big pile of cheese here. It looks like Thanksgiving isn't really over yet. So you've got some analogy here, certainly, to have all this cheese sitting here.
So this is just really dumb, but it's going to make it you remember this. This is why we did this, and I'm gonna be eating a lot of cheese this week. But on this side of our table, we've got materials. We've got our 316, our 4130, our 6061 aluminum. We've got our Gouda, Swiss, Parmesan. We've got some cream cheese here, some brie. These are all different types of materials. Now, if you're going to cut cheese, in theory, you wouldn't grab a cheese grater to grate your cream cheese. You wouldn't grab a cheese grater for your brie. Brie is a very soft cheese in the way that aluminum is a very soft material. We have to change our approach based on what type of material we are cutting. We need to change our approach with a different grade, a different chip breaker for each material that we're cutting. So we've got different inserts here, different styles for different depth of cuts, for different material types. And if we just go to the insert selection page on the website, it's super easy. You can just choose your material type. We've made entire videos on this. Bob has some fantastic videos about this. But I just want to remind you that you would not use certain cutting tools on certain types of cheeses. You wouldn't run the same insert for stainless as you would for standard steel. This is an M in our list. We can choose that under material types,
Yep.
right? And we're gonna have one type of chip breaker that is meant just for this guy. Oh, I should have put it up on this. I might have.
Yeah, you're certainly not going to run the insert that you chose for stainless to cut your aluminum, or vice versa.
Yeah, exactly.
Blow one of them up, and you're gonna cover the other one with melted aluminum, I think.
Yeah, exactly. So if you look at the microscope real quick, the one insert on the one side is meant for steels. If you look at the classification, it's a P. It's meant, the chip breaker, the shape is meant for steels. We have other inserts that are meant for, well, heck, I'll take this one. This is a different size insert, but besides that, the snowflake shape, yeah, it's a huge insert. The shape of this insert, the snowflake shape, it's special. This insert is, I think it's HK20. What is it? Yeah, this one's made for cast iron. So again, we've spent a lot of time going through and selecting different inserts for this guy. You can look at these guys, and there's different chip break styles for different material types. So if you're running one type of material, it's going to break the chips beautifully. Even though they both might be CMG 432s, you might have one that's meant for a stainless, one that's meant for steels and regular like that. And we can go back to the wide camera. So there's a different insert based on your material selection. If you're having problems with stringy chips, you already know what size insert, you're running the wrong chip breaker. We are running the wrong chip breaker. And as operators at the machine, we've got to go and we have to know that and go through these selections and have inserts for stainless, insert for this. If all you were doing was cutting brie all day long, then I might go and I might, here you go, Sal, I might come over here and we'll get the shot of this brie. If I take this wire, this stuff is like...
Does this count as a cutting demo also?
This is a cutting demo. So if this is brie, if I was going to try and cut this Parmesan cheese with this wire, I would break my wire. It's not going to... This is a hard cheese, right? Which is basically, we're calling a super alloy. This is our Haas alloy, our titanium, is the Parmesan of cheese.
Go.
Yeah, and then over here we've got aluminum, which is a very soft cheese. And if we try to cut this soft cheese with a different, it's got a nice rind to it. If we try to cut that same soft cheese with a different type of knife, with a regular chef knife, it would stick to the sides. It wouldn't break a chip. It would not be proper. If we were gonna use the cream cheese, we've got a different knife for this. So again, all these different cheeses.
Yeah, you'd never grate cream cheese with a cheese grater.
We would never grate cream cheese with a cheese grater.
Is cream cheese a cheese?
Is cream cheese?
I don't know. I'm not even sure if it's actually
I should have brought some cheese whiz.
That's definitely not cheese.
You can let us know in the comments if cream cheese is an actual cheese or not. It says it is, or if cheese whiz is a
So we were talking about the HMU grade of insert. How that's kind of that's maybe kind of a special example of this.
Do we
want to talk about that for a second?
So all we're doing here is saying, look at your depth of cut, choose your grade right from the website based on your depth of cut. That's what we're looking at here. Now this HMU is fantastic. If you wanted a nice slice of cheese, I might grab this this cheese slicer here. So if I've got this cheese here and I've got this Gouda, if I've got this Gouda over here, there you go, Sal. If I wanted a nice thin slice of cheese, I haven't tried this, so we'll see what we get here. I'm going to eat this cheese. So this type of slicer is meant for creating nice, beautiful, thin slices of cheese.
Hey,
look at that. I really wanted some cheese. It's amazing. This is really good, thin sliced cheese.
So this insert is exactly that for our material, because your sweet spot's way down here at the bottom, right?
This thing can shave off a paper thin, literally paper thin slice of cheese off your material. Why would you want that? It's going to induce less pressure into your part, less deflection. If you have thin-walled parts, that's going to make a difference. Sal, if you can take a picture of this. Okay, so this is an HAL grade insert. This one's actually made for aluminum. This is a boring bar. All of our boring bars have single-sided, like CCGT type inserts. They're positive rake angle. Positive rake angles are meant for shaving material off. They have almost no pressure on the material. Almost all boring bars have single-sided inserts like this that have positive rake angles because they put almost no pressure on the tool. Because boring bars are sticking out so far, they're more likely to shatter. If you try to run an insert like this guy, a neutral insert, first of all, the insert would drag, but not only that, it's a blunt negative rake angle insert. It's going to force the material sideways, but it's going to last forever. And that's another thing. Let's talk about that. Take a look at this. Take a look at these two inserts back at the microscope again. So what we're seeing here, it's kind of hard to see. I'm going to zoom in a little bit. We'll see if we can get here. And I'm going to actually put a third insert on here. We'll get this guy. This is a used insert. Burnt pretty good. Okay, that's there. We're going to get some focus here. Sorry for that, guys. So what we're looking at here on this insert is I can tell this from looking at this guy. If I draw this line over here, from there to there, the width of the margin on this roughing insert is pretty wide. It might be 10, 12, 14 thou wide, because this is a roughing insert. If it's a finishing insert, and I was to draw another line over here, the margin, which is the edge on these guys, it's got more of a positive rake angle, and the width of the margin on this insert is paper thin. This is probably a 3/1000 of wide margin on this. So this insert is going to take a beating. It can handle a negative rake, but it's also going to put a lot of stress on the material. And for roughing passes, that's fine, but for finish passes, we need a finer edge. Now, this is a worn insert, and it's a much larger one. I don't know how big this margin is. This margin is huge, but this is a 3/4 inch inscribed circle insert, probably a 643. And it's got a massive margin for just beating up against the material. If you had a thin-walled part, you wouldn't be able to live with that wide of a margin. So
you just tear it right out of the, chuck.
How do I get one that doesn't stress out the material? That is the chip breaker. That is the chip breaker on our insert that determines whether we're going to have this type of wide margin or thin one. Is it a roughing medium or finish insert? That type of thing. This right here, I can tell you right now, if it's getting that close, it's gonna be a positive rake insert. It's meant for shaving more materials. Now this particular insert has a very wide range, really forgiving. If you were going to go with,
you want to go to your mixed image here, the two together.
So this is a sweet spot for our roughing insert. This is a sweet spot for our finishing. There's a lot of overlap. You can use the one for everything. So why wouldn't I just use this insert for everything? Well, like we showed you on the scope, with such a thin margin, with that rake angle, this one's going to die pretty fast.
You can cut that deeply, but just not for very long.
It's not going to last as long as the roughing insert. And so this brings us to our next type of part on the screen here, is that we've got our chip breaker. This is what we're talking about today. How do I make better chips? And stick around if you're a programmer, because we're going to talk about another way that we can create stringy chips or avoid them. But we're talking about chip breakers right now. Man, it's all about your depth of cut and choosing the right chip breaker to go with each one. But there's also something at the very end of this guy. Let's say I'm going to make this a 15. This is unique. This is the grade of our inserts that we're talking about. So this is the shape. This is the size, pretty much, the size, shape. This is the shape of our chip breaker and the size of those margins and all this kind of stuff that allows us to go to different depths while breaking a chip. The last number in our formula here that we've just got to know is how hard the chip, or it's what coatings are on there. Now some coatings are meant to be slippery for aluminum or this type of thing. Other ones basically are how hard the insert is. Is it
resistant to heat and abrasion?
Yes, exactly. And that's kind of going to bring us to our, this is really dumb. But take a look at this. What I've got here on this screen, I'm going to put these guys over here so Sal can see them. So now we're talking about different grades of inserts here. If I was to look at this right here, if I was going to cut cheese with this right here is an ancient Indian artifact, right? It's not an arrowhead, but a spearhead. It's made out of obsidian, and it is extremely hard. And this is what people use for thousands of years as weapons and cutting tools. They would chip out the edges. And I almost don't want to show you this, but I'm going to anyhow, because it's going to make my point. Let me clear this guy. If you choose the wrong insert grade, do I have a broken chip here? Sure. Oh, there's right there. Okay, so this is more of a notching issue there. But you can see the way this guy chipped on this insert. Let me zoom in. I'm going to zoom in, and then I'm going to refocus for you guys. Be right back with you. Okay, so this is a notching error, but also looking at this damage to this insert, this is not normal wear. This insert chipped in the same way that, and we can go back to the main cameras, in the same way that our obsidian is chipped on the edge. We're probably using too hard of a grade. Now, I went with an HTP 15 because it's a super hard grade. And if we go to the website, you can see the underneath grades.
Yeah, right
look at that. Scroll down to the bottom. Keep going.
Whoa, where are we?
Oh, that's okay.
Yeah, there we go.
That's okay. So there's a spectrum here. Oh, go to the speeds and feeds page. We'll just show the speeds and feeds.
Okay.
And in a moment, stick around. We're going to talk about different ways you can program your parts to avoid these stringy chips. We're kind of covering the basics.
Is this what you wanted?
Yeah,
or
you can zoom out and scroll to the very, very bottom,
okay.
the surface footage section. So even right here, this is all for steels, this type of stuff. So there's different types of grades here. 15, 10, 15, 25. Oh, that's funny. The order is a little wonky here. It's funny. But basically, for us, for Haas, the smaller the number, 10, 15, 25, 35, the smaller the number, the harder the insert is. And so why would I want a nice hard insert? If you're not doing an interrupted cut and you want a nice hard insert, why would you want that? Because it's going to last forever. It's like running a 200 mile per hour tire, right? It's a hard tire, it's going to last forever, but it doesn't grip in the corners. So we want a nice hard insert because it allows us to run a higher surface footage. This HTP 15 on our steel can run 1,400 surface foot per minute right here, which is incredibly fast on certain material types. If I want an insert that is not going to chip like my obsidian, then that's going to be indestructible, I mean just unobtainium, then I would go with a different type of grade insert. So if you're getting any chipping on the side of your inserts, you've chosen the wrong grade insert. You need to find a tougher grade insert that's not going to chip on us. But if we can get away with it, if we can choose an insert grade that's harder, like an HT, like a 15,
it will tend to wear longer.
We can double our surface footage, run the parts faster, and make it. But if you start chipping the inserts, then you've gone too far. Go back to like an HTP 25 or an HTP 35. It'll be a bulletproof insert that's going to not chip on you, but it is going to wear out faster. But then again, we want it to wear out, not catastrophically fail. So if you're chipping inserts, you might be programming it wrong. Or this.
So why do you have that old cell phone there?
So this is it.
You just had to throw that in there.
I love this. We're going to end here with, we're going to talk more about the programming style. But this right here is hard to find. This is a classic item here. This is a Nokia 3310 in Europe. It's a 3390B is my phone here in the States. And this right here, they've got memes all over the internet about this phone. This is the Chuck Norris of cell phones. Now this phone first came out in 2001 or something, I don't know when it was, a long time ago. It is bulletproof. This phone can be dropped and dropped and dropped, and it's got a plastic body. Pop the battery back out of that. But it can be replaced, and it's right here. You can beat this phone to pieces. You're not going to scratch it. You're not going to break it. It's going to keep working. But
no glass probably on it.
It's not
anywhere,
no glass. My iPhone. Now I want my iPhone. I love it. It's beautiful touch. But if I were to drop it, I'm not dropping my phone. If I were to drop it, it would shatter. So my first choice is to go with the hardest insert we can get because it's going to last forever. But if you have an interrupted cut, it's just going to chip your insert and that's it. Oh, I love this. So this is the Chuck Norris of phones. We want to go tough with our inserts like this. So again, the hardness of the insert is just about the material type that you're running and how long you can get away with it. If you can get away with hard, go with a hard grade insert. If you're buying a universal insert that you're going to use for anything in your shop, start out with like an HBT 25, middle of the road insert, because you don't want it chipping on you. If you're running a production job, I would buy some of those harder grade inserts, run a few of them, see if it chips on you or not on the material that you're running. And if it doesn't chip, you're going to find out that your tool life is fantastic, and you can double your surface footage based on our speed and feed chart. So a lot of these things, just go to the website. You want to buy the right chip breaker to avoid chips, and then you want to go with the right grade for production. That's more of a test and see type of thing. But if you're just buying inserts right now, because it's a holiday sale or what have you, and you're just buying a bucket load of inserts, maybe start with like a 25 or a 30 or 35, because those are going to be good solid inserts. They're going to get you through the job. And then you go with a 15 if you're running something a little more production, and you're able to test.
Like you said, you're going to run that and see if you can. If you're not going to chip it and you get the life, then it's going to probably give you more run time.
Yeah, because you can run twice the surface footage in some cases by running a harder insert. But like my glass phone, you're risking a chip, and that's not good. I was going to show you something else here about.
Yes, you were going to talk about for operators and programmers.
Okay, so this is operators and programmers. Operators, you need to understand your chip breakers and how those work, and you need to understand your grades as far as tool life. That's it. If you run too fast on an insert that's not built for it, if you run too fast with a tougher insert that's not hard enough, you're going to smoke the insert. That's going to kill your tool life. If we look at my cam system here, though, I'm going to show you how I programmed this part that I was running the machine earlier. Now, this guy's pretty cool. We can run this guy and show you what it's running at. This is just our depth of cut there. Let me jump ahead to the finish pass. What I want to show you here is this is the way that I would normally program this guy if it was going to be like a G71 or type of pass. Look how it starts on the very face of the material, and it comes in and then it comes over. It's going to do it all in one shot. We're going to watch this guy run. This is a finish pass. Now this is how a lot of us have been taught to program in school and when we first did it. This is a G71 single pass. It comes up and over and it runs. The problem with that is that the chip breaker on the insert only works on this one edge and not the other edge of the tool. And we've got a video for you that's going to kind of show you this. Let's go ahead and we'll go to the video here and we'll show you how this works. If we change the style of programming, this is using a G71 type of pass. Oh, sorry, this is the other pass. We've got no drag and drag. Do we have the other video? Or are we showing this one first? Oh no, we'll go back to that one. Do we have the shot of the tool path going in one shot? We'll show the drag tool path. Okay, so this is it. Such a drag. So Lee, if you look at this guy, this is how most of us program with the G71. This is our contour. The insert's going to come from the face. It's going to go up and over and run there. And go ahead and run this video, and we'll see what this looks like.
From the beginning or from here?
From the beginning is fine.
Okay.
Thanks, Frank. So this is a normal G71 cycle. And look, right here. Oh, that's okay. So this has both cycles in it in the same video? Oh, perfect. Okay. So what we're showing here is a no drag cycle. It's facing down the way the chip breaker was intended to be used, and there are no chips there. Now, as it comes across the face of the part, it's breaking the chips like it should because that's the way this insert was built for its depth of cut, this type of thing. Now, on the flange, like if this was a crankshaft hub or something like that, watch the way this is programmed. It comes up and over and then down. And again, it's breaking chips. All those chips are going to make its way through the chip conveyor. This is a way we should be programming our parts. And in a second now, we'll show the other way. This is the G71 way, where it's dragging across the face. So this insert is hitting the front, and look, it's creating a little bird's nest there. It couldn't break the chips because we were using the wrong end of the insert. We were using the side of the insert. And by having one continuous tool path, we are gonna get chips as it drags that insert up against the face of the part.
Whenever you're using the trailing edge, You're cutting at a much different angle than you are with the leading edge.
Yes.
As it were.
We're,
right?
we're using the trailing edge, dragging the insert. Look at this.
Now it gets crazy.
And this is getting a terrible bunch of chips, and that's gonna be unavoidable if you're using a G71 type cycle on certain types of parts. Oh, and this is perfect. Look at that. So, look at this at the end. See those chips right there? That was created because inserts are dragging, wrong depth of cut. So it's not always the insert's fault. Sometimes it's the programmer's fault, and I know because I'm the programmer. If we just change the way that we program, we can fix quite a bit of this. If we can cut back to my simulation on my laptop, we'll show you this guy.
And part of what you're saying is that insert is never gonna cut correctly if you're dragging it.
If we're dragging, it's never going to cut correctly. In fact, right now in the software, look at this. You can see it turned red on my holder because it's telling me like, hey, buddy, you're not even using the right side of the insert. It's got too shallow of an angle. It's going to cause problems. And so look right there. You can see what it did right there. That's not the way it's supposed to cut. I'll rewind this. Look at this. It's dragging this insert across the face of this part. And that's going to create stringy chips unless we quadruple our feed rate, which would be a real kind of hassle. I'm going to exit the simulation now. I'm using Fusion 360 software. There's lots of other softwares out there. I'm going to change my tool path here. And amazingly, there's something here in the software for my finish pass that's actually called no dragging. And what it does is it hops over like the video showed us, and it's going to change the way that we approach this part. Now, if I run the simulation on this, here's the exact same part. All I did was press one button in Fusion, and now it's going to change the way it approaches. It's not going to use a G71 cycle for the finishing pass. It's not going to do it in one pass. Now it's facing down the front, using the chip breaker the way it was intended, the way God designed it. And so this guy's coming down across the face of this part. It'll break the chips beautiful, just like our video showed us. Then it's going to come across the front of the part, which we already saw that if we had chosen the right chip breaker, it's going to break chips for us. This is huge stuff for programmers to know, huge stuff for operators to know. Now right here, we're going to come against this wall, right? And it's going to make a big mess of chips. It's going to ball up right here as it drags the insert across the face, right? But no, wait a second. It avoided that. The software is hopping up and over our part. I could speed it up here, and it's hitting this thing the way the insert was intended to run. It'll come down there. No more stringy chips on that pass. And that's just the way it was built. That's the way the insert's meant to cut. And so with one simple change in the way that we program our parts, whether you're programming by hand or programming with CAM software, we can avoid chips again. So avoid chips. Change that depth of cut to match the insert, or change the insert chip breaker to match your material type and depth of cut, or change the way that we program our parts and avoid stringy chips. This is lathe turning 101 that everyone figures out on their own eventually after pulling chips out of the machine for years, and they finally realize what's happening here, and that the chip breaker on our inserts is critical. It's just so important for what we do as machinists.
So we're probably gonna wrap up with some kind of more general information about insert life and that kind of thing. But let's take a couple of questions before we do that.
Yeah.
Put you on
if you have a new question, get it in right now.
Yeah, put you on the spot
here. Put it
here.
in the comments before we shut off here in about 10 minutes.
Okay, so Benjamin East asks, I am struggling to run the recommended depth of cut due to chatter on an 8-inch bar, 8-inch long, 1.125 bar stock, I'm assuming diameter, using a tailstock. How can this conversation incorporate managing chatter?
In general, chatter's just a big issue there. So if you're running a tailstock, that should help quite a bit, right? It adds more support. But again, the more stress that we're inducing into the part by using a negative rake angle insert, the more problems we're going to have. So generally speaking, as a general rule of thumb, if you want to avoid chatter, bury that tool. You want to increase your feed rates, you want to increase your depth of cut to a point, and you want to make sure you're using the right chip breaker.
As you were mentioning, the tool pressure is partly
Yeah,
partly influenced by the
some
insert.
skinny parts, especially as your part starts getting skinnier and longer, you can no longer run a negative rake angle insert. You have to switch and not, the reason we go with a CNMG insert, a CNMG insert is kind of double-sided. We can run it this way or that way, but again, it's kind of dragging across the face of the insert. Here, Sal, if you come over here for a second, I'm going to give you a real quick picture of this guy. This is our Gouda. Man, I want another piece of that Gouda. Now, for this guy, this is a cheese grater. This is our cream cheese. We're not going to grade that. So this is a sharp cheddar cheese. And if we can get inside here, I'm going to try and grate some cheese for you. I'm going to take this guy, and you can see that this is a positive rake angle on the cheese grater. If I take this guy and I grate it this way, you can see that it's cutting pretty good. Now, what's odd, this is like a CCGT insert. It's got a positive rake angle. It's putting very little pressure on my material. It just kind of cuts in like that. Now, what if I want to go with a negative rake angle to cut this cheese? I'm going to take this cheese, I'm going to go the other direction. And I'm pushing really hard, and it's not cutting right, and it's putting a lot of effort in there. I'm not getting anything. It's just not the way to cut cheese. We don't want to be cutting with a negative rake angle on material. It's inducing more stress in there if we've already got chatter. Go try a positive rake angle insert. Go with like a CCGT type insert like we use with our boring bars. See if that helps. Otherwise, you can kind of either play around with your speeds and feeds. And sometimes increasing the RPM is what solves the problem if you're getting some chatter like that, which is crazy, I know, but there's resonance issues there. So try bumping those RPMs up, which is crazy sometimes. Normally you bump the RPM down, the surface footage down to avoid chatter. You increase your depth of cut, you increase your feed rate to avoid chatter. But if you're getting stuck, throw everything out the window and try bumping up those RPMs, seeing what can happen.
John Nelson just piped in and said SSV.
Oh yeah, the G38 and the SSV.
Yeah.
You made a terrific video on that.
We did a long video on that years ago. But yeah, that's
Thanks.
another thing to try.
Look up SSV, Haas SSV, go on YouTube.
Spindle speed variation.
Spindle speed variation. And it oscillates the RPMs, which avoids resonance with the part, especially on long parts like that for tail stalks. Absolutely.
Yeah.
Thanks, John.
So we, since you just went back to the cheese there, we'll jump to this next comment. Dan Robles asks, Mark, what is your favorite cheese? You've got a lot of really good ones here.
Exactly. You have to have the right cheese for there.
You really don't want to make that decision, right? You just want to have all the cheese.
My favorite cheese is probably, and again, I'm choosing the right grater for this, is probably a Parmesan. So if I've got my Parmesan cheese, this is one of my favorite graters right here. If I take this guy, again, you would not be using this with a cheddar. You wouldn't be using this with
imagine the mess.
Whatever.
That would make.
This thing's, oh my gosh, this on spaghetti right now would be fantastic. Or you can just take a chunk of it and it's brittle, right? It's just basically fall parts. So you can use a chisel, this type of thing, cut this guy open. But definitely a real aged, 36-month, 48-month Parmesan.
Oh wow, that sounds amazing. Okay, one more question for right now, or maybe comment and question. Larry Blount asks for more videos, I think, on smaller machines and roughing insert selection with speeds and feeds. In particular, in his case, I think the TL2, where he's struggling with 17-4.
Oh yeah, for sure, right? Same type of thing. So it becomes a mess. 17.4, you have to be careful. We didn't talk about this. Depth of cut is super important. So like when I think 17.4, like some of those stainless, I cringe a little bit. If you don't, years ago, it took years before like the tool reps started telling us this, but we knew this. You want to take a depth of cut, at least the depth of the radius. It's not always possible. But if I have a number 2 radius, the 031 thou nose radius, you want to go typically, the depth of the nose radius. So a 31 thou depth of cut is my minimum depth of cut. Otherwise, the tool's just rubbing. Now, I go shallower than that all the time. So it's a rule that we're supposed to follow, and I break it all the time. But if you're on a stainless like that, stainless is notorious for work hardening. And so if you are rubbing that material, you're trying to take a finish pass, and you tried to use the wrong insert, you tried to use a medium or roughing insert, not only is a chip not breaking, you are inducing stress into that material, which means you're work hardening that material with every pass. So pass number 1, it cuts, and now the material that's left is 10 Rockwell harder than when you started. And you hit it again, now that's 20 Rockwell harder than when you started. And you hit it again.
And it's destroying your insert.
And it's destroying the insert. You're work hardening that stuff because you're not cutting, you're rubbing. And if you're not breaking a chip, you're rubbing, not cutting.
It's kind of funny. You're kind of forging that material as you're not cutting it.
Yeah, you got.
So you've got to go deep enough to create a real useful chip, and not smush that material into the base bar.
You can sneak up on aluminum. You can smush it in there and it's going to be fine. You can shave it with a nice positive insert. But if you're trying to do that with a super alloy or some stainlesses, this type of stuff, you are going to work harden that material. So go with a more positive insert on some of that stuff. Make sure you're using something that's got a grade that's meant for the material type, which is an M for the stainless. And make sure that you're running. This is super important for that. I didn't even think about it. It's
funny because this actually kind of drops us right into the final point you wanted to make about maintaining tool life and stuff like that. You were going to talk about smoking inserts. What's going to lead you to smoke an insert?
So in general,
and what was smoking an insert means what?
So if I try running an insert at 2,000 surface foot and it wasn't made for it, I'm going to smoke the insert. It's going to last minutes. By sometimes the difference between an insert that lasts 2 weeks and 2 minutes is 10% difference in your surface footage. I'm not kidding. I've had inserts where I reduced the surface footage by even on aluminum castings and stuff. But you can have an insert last forever just by reducing the surface footage just a little bit. RPM smokes inserts. You have to find that sweet spot just below it. But if you cross that line, the insert coatings start to melt. the insert starts to deform. You've crossed the boiling point, right? You've crossed this line and your insert life just goes out the window. So
it's really funny. Res 441 asks, does changing the spindle speed affect the durability of the insert? And it's exactly what you're saying. You're saying that you can potentially sometimes drop the spindle speed a little bit, or SFM, and get a dramatic increase in life, right?
Yeah, if you're wearing out inserts, it's just you look on the side and it's got wear marks on it. It's just not lasting that long. It's typically reducing your surface footage that it's gonna make the big difference there. Your depth of cut and your feed rate, we normally don't go deep enough. We can push those things a lot harder than we often do, especially when we're new. We're chipping inserts and we're like, oh, I'm chipping inserts. I'm gonna slow it down. I'm gonna do this. No, we'll probably have the wrong grade. Go with a tougher insert. Again, Nokia is tough. My iPhone is hard. So the insert's going to last longer if it's hard, and it can go faster if it's hard. But it's going to not break if it's tough. But it may wear out sooner. So you can't run HDP 35 insert at the same RPMs as an HDP 10 or 15 insert. This one can run higher RPMs and it should last longer unless you're chipping it, and then you have to start working your way this way for the toughness. Interrupted cuts, if you got a keyway, forget it. Just start out with an HDP 35 or whatever grade.
Right, because you're already slamming that thing
you can't
to begin with.
Well, we didn't talk about, so we've got some beautiful like PCD or like CBN inserts, which are fantastic for some cast irons like that. Those inserts last forever. They're fantastic. They can run incredible RPMs, surface footage. But if you try running those type of inserts, those type of PCD CBN inserts with interrupted cuts, they'll explode. They'll chip. They cannot handle interrupted cuts because they are incredibly hard. They're like diamond hard. They're diamonds, and so you got to avoid those inserts on interrupted cuts. But if you got a part that has no interrupted cut, and you got the right materials, then oh man, you could really increase your tool life.
So you showed that insert a few minutes ago that had the notching in it.
Yeah.
What's the issue usually when you have that? When you have notching, what are you looking to fix in that case?
So notching is typically a matter of notching, generally speaking, is you're taking the exact same depth of cut, and that's where the first impact is, the point of contact in the material, and it's happening over and over again. Typically with notching, I would go with a tougher grade insert. Simply, I'll just go tougher grade insert to avoid that chipping. And I've got some inserts here someplace. I think I hit it because I didn't want it to be on camera, and now I want to show it. Yeah, the inserts will actually chip just like the obsidian knife over there. You'll literally see chipping on the side of your inserts if you're running too hard of an insert. So if you're running that, you got to go with the
Usually
tougher
not
grade.
a tough enough grade.
Not a tough enough
what you're
grade.
saying. Okay.
Yeah. If you're notch, yeah, that type of thing. You can also adjust your RPM one way or another. Sometimes that type of notching or something like that might actually be that you're running the RPM too slowly. You're getting a built-up edge, which means the material is sticking to the material. And it's got built-up edge, built-up edge, built-up edge because you're not running it fast enough. You got to increase the RPM to build up some heat so it doesn't stick. And then sometimes that built-up edge will actually catch and break and it'll chip because of that. Mm-hmm. So sometimes the chipping is actually not because it's too hard, it's because you're running too slow of an RPM, you're getting a built-up edge, which causes a failure afterwards as well. So,
one of the things we were talking about a couple of days ago was the difference between appropriate wear and problematic wear, and how you tell the difference. I mean, when you are done with an insert and it's done its job correctly, what should it look like? You're looking for even wear across that cutting edge, right?
You look at this guy. This is a beast on my microscope. I'll probably turn this insert sideways and refocus, but I'll show you the face of it first. So this insert right here was run on cast iron, and we run the heck out of these inserts. Now this is a kind of middle of the road grade as far as hardness. Let me flip it over, see what this guy looks like. Okay, so this thing's kind of a normal wear. I want to show you the side of the insert. Sorry for if I'm making you sick right there. I'm going to change my focus here and give you something. That's better. Okay, so this insert right there, you can see I'll change my focus here, but this is kind of a normal wear insert. We've gotten everything we could out of this insert. So on the edge of this guy right here, this insert right there is kind of standard wear. It got more and more worn out until it started leaving a burr or doing whatever. Maybe it was taking a little bit more horsepower to get to the cut. That is normal wear for me. So whoever ran this guy, I'll give him a raise.
Set correctly.
Dude, whoever's running this job, this was from our own machine shop, is exactly what I want to do. I want to see an insert that is dead, that is like on its last leg, but they've chosen the right grade. This thing's hard enough to take this kind of wear and not explode. It's not going to catastrophically fail when it gets to this point because they've got the perfect choice for grade and toughness and hardness. And so they can run this thing and get the full tool life out of it. I love this insert. This is showing perfect wear for me.
Right. So you're going to have gradual
now this,
rounding and degradation of the cutting edges, right?
We'll show you this guy. This is terrible.
So
this is one. This right here. This is horrible, right? So if you look at that right there, that was my fault. I was using that G71 cycle coming in and facing, and let's show the video on this. Frank, do you have that finished cycle video? The finishing. We'll show that video one more time. You can just.
With the two top to bottom or the cycle?
The cycle ones, yeah. And again, we'll just look at the chips on this guy. So by coming down the face, any grade insert can handle this. It's all the same way. So this is a nice solid part. There's no interrupted cuts. It can handle this. This insert can handle this just fine. And we can speed up and kind of go through this one, Frank. So it looks beautiful, and we can go to the next part. I chipped this insert. Oh yeah, so we'll go to the drag. Okay, yeah, so then we'll start this one over. And so, okay, perfect. So this insert is too hard of a grade it's too thin of a margin. So as the insert came in on that front side, I had left like 12th stock. This insert was too hard and I chipped the edge of it because it's brittle like that obsidian knife. And so I chipped the insert by coming in sideways too fast and it just broke the insert. I left too much stock in there. I might have left 20 thou or something, I don't know.
You've talked about that. So that's one of those examples of if you have a lot of variation part length wise, where you might be taking an extra deep cut on your first facing cut, maybe you can't use a weaker insert, so to speak, right?
Yeah.
Because you might experience a heavy load you weren't expecting.
Yeah, even with that tool path and the amount of stock on there, this type of stuff. And as far as this could be 4140 heat treat. I don't know. I just grabbed this material, but what's funny is if I'd gone, well, I did. If I switched to a harder grade insert, no problem at all. It ran just fine, and that's when we got that video. I swapped out to an HTTP 25, and even with like 15 thou of stock on those faces, it just ate it just fine. But it was too much of an impact for this grade of insert.
Right.
With that type of cut. Now, with the right tool path, it ran all day long with this same insert.
We have a couple more questions.
Yeah.
APM Engineering asks, I just bought a new ST20Y, which will be installed in 2 weeks.
I love that machine.
Is there a starter set of inserts to cut stainless, alloy, and steel to find my way in turning?
Well,
Hey, it's a perfect advertisement for Haas tooling, right?
Yeah,
of course there are.
Just go back to the insert page.
Yep.
So this is, again, it comes down to like, different levels and horsepower.
Which
so if we
one
go to the
do you want to go to
page,
insert styles? Or?
Well, if we can scroll down, we can actually let's use the filters.
Okay. Yep.
So if we just come down to, click on stainless, instead of steel.
Yep.
And we'll click off of stainless, we'll click on stainless, we'll deselect steel.
Unclick steel, yep. Okay, there we go.
And then let's go ahead and click on a C shape towards the top.
Yep.
Yeah,
okay,
C
so
style,
there's our 80-degree rhombic.
Yeah, so we can look at that. And so what we're looking at here is there's different grades, like an HUM or something like that. It's kind of a middle of the road. So let's just click on this guy real quick.
Okay. Like this right here?
Yeah.
Okay. Let's open that over here.
And scroll down till we can see like the P, PMK, stuff like that. So right here, this thing's made for stainless. Now if we go up a little bit so we can see the picture of the insert. This is a weird, look at this. This snowflake shape is completely different than what we saw earlier. It's a different type of insert. Now, if you open up your feed and speed chart.
For this one?
So this is actually what I'm saying is kind of a good middle of the road. Yeah, speed and feed chart. And let's find HUM. I don't know where they are. We can find it. So we know that we're going to run on stainless. It might be on the next page, right there. So this is kind of my normal middle of the road thing. So this insert, I can already tell, this thing can handle, it's going to start breaking a chip at between 20 thou and 160 thou, which is pretty good for me. So if I'm running that thing at an ST20 at 80 thou depth of cut, 100 thou depth of cut, 120 thou depth of cut, it's a decent insert. It can handle this all day long. There's my feed rate, my feed per rev. I'll start out, 8, 10 thou per rev. I'm going to start my depth of cut. At 60 thou, then 70, 80, 90, 100, 120, see what I can get away with depending on your machine. But again, this insert is not, like the inserts I was running were for P. P is the code for steel. M is the code for stainless steel, but the website is pretty cool in that it does all that work for us. So we start out there, but then you can't just stop on the website for the selection. You have to come to the speeds and feed page and look at your depth of cut and decide what type of chip breaker do I need for my depth of cut? And then you'll find another one.
Right. What depths are you expecting to cut on the parts?
And that's underneath the filters as well. We can go to the filters and you can look under different chip breakers. There's an entire section underneath the header which explains all these different chip breakers as well. But I live on the speed and feed page, which is awesome. And I also live on, here, if we zoom out and we go down, and let's find an HUM. So this is all, look, so blue steel. Let's go down until we find the M stainless.
Keep
going. So there's different grades of steel. We can find out the different grades that we're going to find on there with different chip breakers. Now, based on your material type and your depth of cut, we can choose our grades, and then you can decide if you need a finishing insert or roughing insert for that. But there's a big difference in chip breakers for stainless versus standard steels. We have some inserts that are okay at everything, but it's just like anything. We have a universal insert that's okay at everything, but it's not great at anything. Because it's a general insert. I would have that in a job shop where you're doing prototypes all day long and you don't really care. You just choose a tough grade and run all your parts with the same insert and it's fine. But if you're running production on something, you got to get the right grade.
Right. That may be what they're looking for to start with, is kind of a generalized insert that can do everything.
I'll mention that. So 10 years ago in Canada, Oklahoma, I was at a customer, and he had been fighting tool wear for weeks on a brand new machine. He'd had a brand new ST20Y. And a young guy in his 20s, 23, and he was about to go out of business because he hadn't made a part in 2 weeks. And so we were there doing some training. We went to his shop. He kept programming things funny. Long story short, we checked the coolant level. Here, we'll show this. Sal, we'll bring over our
yeah, this is where the insert and the machine have really nothing to do with your issue.
Yeah,
right?
this is, so again, like sometimes it's the chip breaker on a machine that's causing our problems, and like we showed you, sometimes it ain't the chip. Sometimes it's not the chip breaker, sometimes it's the way we program the parts that cause the problems. And other times on stainless, you said stainless, that's why it's in my head. This poor guy must be a millionaire by now. If you're this young guy, I went to his shop, I walked in, he said he'd checked everything, kept breaking inserts, kept wearing out inserts, so I believed him. Obviously he knows what he's doing, right? He's smart, he looks at the catalogs. And so first thing I did is I pulled out my refractometer, and here, go to the website of this thing too. We'll look at, see what the refractometer is. This is a refractometer, and it measures the coolant concentration, and on stainless and some other materials like that, it is just critical, super important. It measures how much the light bounces through different materials, this film. We made a great video about this one. Sal, we made this video. I love that video.
A few videos.
Go watch that dumb video online for refractometers. It's fantastic, and it's got no views. No one cared. I love that video. But a refractometer tells you our coolant concentration, and his coolant concentration was at 2%. Was at 2%. And so we grabbed some coolant, we dumped it in there, brought it back up to 8% coolant concentration. He pressed go. He made parts nonstop for the next hour I was there, and he was about in tears. And I left that man with my refractometer. And so someone out there in Oklahoma's got my refractometer. But again, go to the website if you haven't got one.
Yeah, so right now it only costs you $19, pretty easy.
Yeah, when it comes to tool life, you can't go wrong with just measuring your coolant as well. There's a lot of pieces to this. It's like a PhD in machining. I think we're underappreciated as machinists and programmers. There's a lot to this stuff, but the website does make it pretty easy. As long as you know which pieces are involved. Don't forget this part of the equation here as we're kind of wrapping up and finishing things off for the day. Again, this is only half the story. CNMG 432. This is only half the story. This is the other half of the story. So critical, so important. It's the difference between running a machine with a bird's nest like this guy, or running it, with beautiful chips that can actually make it through the chip conveyor. That's what this video was all about.
Yeah. Thanks a lot, Mark. That was awesome. If you guys have further questions, drop them into the comments on this video after we're done with the stream. Of course, this will post to our channel. You can rewatch it there if you want and add questions there, and we'll try to get to those as well.
Yeah, that's about it.
I think that's about it.
Thanks for letting us be a part of your success. We're going to eat some cheese right now. Go check out HaasTooling.com, the Haas CNC website. Check out those filters. Spend a few minutes looking through the great literature at the top of the insert page, which will explain this much better than I could have here today. But just realize there is a difference, and it really affects the way we make parts.
Thanks so much, guys. See you soon.